Yeah.
Hey, let's take a look. Okay, I wanna just quickly review something for you. We got two more little sections to cover, and then we'll be, sort of done with the review part. We can start moving on to some newer material. Piecewise functions. Now you've done some stuff with these, but I bet you this is also an area where maybe I've done a lot. Very important though. Piecewise functions are. What do I got going here? Got a little background. Piecewise functions are functions that are useful because we can use them to define things that have different behaviors at different times. Like just as an example, let's say we were going to try to make a mathematical model of a skydiver's height as a function of time. Now, when he jumps out of the plane, what's happening to his, really there's some things that are happening there. What's happening to his height as a function of time when he first jumps out of the plane? When he jumps out of the plane, he's not falling at all, but he starts to drop. Talk about that a little bit. What's going on? Imagine yourself in that situation.
Gravity's pulling on him, but the plane's...
Okay, so, and we're only going to worry about the vertical part, so we can ignore the horizontal part. Maybe it's a helicopter he's jumping out or something like that, or jumping off a balloon, stationary balloon. But what's going to happen first? Yes, sir?
First he has to jump into the air, then...
Okay,
So
once he jumps into the air, what's going to happen?
first gravity pulls on him, down to stop, then drops.
Okay, so gravity's going to pull on him the whole time, right? It's going to accelerate him down, so wouldn't you agree he's going to pick up speed pretty fast?
Yeah.
Okay, does he accelerate forever? No, he doesn't. If you think about this, he only is going to accelerate, he's going to accelerate the whole time, but he's only going to pick up speed for just a little while. And then what's going to happen? Okay, but even before he pulls the chute, and this is kind of important, even before he pulls the chute.
He hits some
Okay, now listen, I can't have talking. I need you guys with me, please.
terminal velocity.
Okay, good. There you go. He hits terminal velocity. Okay, so after a while, as he's falling through the air, the force of the air on him, as it's blowing by him, is going to offset the gravitational force, and he's going to end up coming to some terminal speed or terminal velocity where he's not going to go any faster. And for a skydiver, I think it's something like 120 miles an hour typically. Once he gets to that speed, he stops, and he's just going to cruise down at that speed for a while. But that's different than what started off happening. It started off, he was accelerating pretty freely until he got to that terminal speed, and then his velocity stays the same. So those are two different kinds of behaviors already, aren't they? Right? And so we would need a function. If we want to describe this with a single function, we already need a function that's capable of handling two different types of behaviors at the same time. Now something radically different happens. He pulls the ripcord, and the chute pops out. What happens then?
His velocity slows down.
Yeah, okay, for a short period of time, he's going to decelerate, and it's going to pull on him pretty hard. So he's going to kind of decelerate, and then once he decelerates to a certain speed, he's going to come back to a new terminal velocity that's a lot slower, right?
Yeah.
So really, we got four different kinds of behaviors going on there. If we want to describe that with a single function, we need a single function that can handle four different behaviors at a time. Well, this is the kind of function that we would use for that, a piecewise function. Okay, so what does a piecewise function look like? What's it do? Like we just said, in real life, sometimes we need to accommodate different behaviors at the same time. So this is what it looks like. Actually, that little line in the middle wouldn't be there. Ignore that.
Shall we write this down?
I don't think you need to. I don't think you need to. It's in the book. It's, this is going to be, this is available, and you guys, I'm going to start checking. I want to see people using these resources. I want you to get in the habit of knowing where they are and using them. So you know where the PowerPoints are, but even better, everybody knows now that the YouTube videos are up, right? Those are the best. I mean, if you need a quick summary of something, just go look at those. Okay, so what's this mean here? Well, we've got a single function, f of x, that's got two different behaviors depending on the x values, right? You remember this stuff? Remember seeing these? Raise your hand if this looks pretty familiar. Okay, raise your hand if this is not looking very familiar at all. Okay, that's all right. Doesn't matter. That's fine. So one equation, the top one, is going to give us the values of f of x. It's going to predict the values whenever x is less than or equal to 1. And then the other function kicks in when x is greater than 1. So what if we want to evaluate a function like this when x is 0? Think about that for a second now. How's that going to work? If I want to evaluate the function when x is 0, first of all, talk about this at your table. What's the number? What is the value of the function? Remember what that means. When you hear the word evaluate, when you're being asked to evaluate a function, you automatically shift into number mode. You know that the answer is going to be a number, single number. Okay, I want to know, what is that? What is the value of the function? In other words, I could write it like this. What is f of 0? Okay, talk about that for just a second, and we'll see if we can. What do you think? Why don't you guys team up here? You two. You guys.
Does it mean all x's equal 1? That's what I'm understanding. F of x is basically y, right?
Mhm.
Okay, so y is 0. Means it's
You guys talk about it.
indefinite.
Yep.
Or not indefinite.
You're right. Can't it? You're absolutely right. That's a good point. Then maybe you don't use the top part.
So you use the top function.
Okay, well let's talk about this first one. Any ideas? Now, when we do something like this, I want everybody to make sure this is really important, that you understand, you have a really solid idea of what that means, right? Remember that when we're talking about a function here, this is the notation we use. This is our function notation, where f is the function, right? That's what we're naming the function. And x is the input variable. So what this is saying is, for input values x, the function is doing this formula. Well, there are two different formulas, right? Depending on the domain. Now, when x is 0, which part of this piecewise function is being used?
The bottom one.
The bottom one? How come?
Because it makes the
Say it again, the bottom one would be used when f is 0. Why?
because it makes the bottom equal.
The bottom, it does? 0 is greater than or equal to 2? Right? If we're plugging in 0, yeah, it fits in. Now, you see what? You see this part, it fits into that part of the domain, right? Does that make sense? So for x values less than 2, this is the equation that we have to use. That's the function is defined as x plus 2 for all x values less than 2. So when x equals 0, that's certainly less than 2, isn't it? So we've got to plug it into here, right? That's the formula we use. So f of 0 would just equal, would equal 0 plus 2, right? If I plug it in, which is just 2, right? Okay? So you always have to figure out which equation to use first. Now, you're never going to use both. You could never possibly use both, because if it's a piecewise function, if it's a function, the graph can never overlap vertically, can it? Right? So there's always only going to be one equation that's activated at a time. Always. You just have to figure out which one it is. So when x is 0, it's up here. Okay? Fits into the top one, so we get 0 plus 2 is 2. Okay, now what about the next one? What about if we're going to evaluate the function at 2? Okay, that's going into the bottom, isn't it? Because 2 is not less than 2, but 2 is greater than or equal to 2. It's equal to 2, right?
Right.
So we plug it in the bottom. Okay?
Okay, so basically the question is going to be asking us if it's bottom or top.
Well, now, and there might be 3 or 4 different behaviors. It's just going to ask you, in a piecewise function, when you're evaluating a piecewise function, first you got to decide which is the part of the function that you should use based on the domains, always based on the right part of the function. Okay? And then you just evaluate. Okay? Now, one other thing too. In this PowerPoint, they use the word if there. We don't really include that. Usually that's not there. We just have a comma and then maybe a space that separates the function from its domain. Okay? And then of course at 4, which one are we plugging into? The bottom, yeah, okay, so. Okay, now what about graphing it? Okay, what do you, now think about this. If we're gonna graph it, remember that each of these behaviors, only one of these behaviors can operate at a time, right? Now where is the top behavior going to be graphed at the top? We've just got this line with a slope of 1/2 and a y-intercept of 3/2, right? But we're only gonna graph that. If an ant is walking along this function, he's only gonna be walking along that particular line when x is left of 1. Less than 1 means to the left of it, right? Make sense? If his x value is greater than or equal to 1, he's jumping onto a different line with a slope of -1 and a y-intercept of 3. Right? Get that idea? Okay, so yes. So there's actually 2 lines that are going to get graphed, but the top line, we're only going to put our pin down, so to speak, for values of x less than 1. Right? That's where that top line stops. It's defined, it goes on infinitely far to the left, but if an ant's walking along this line from left to right, as soon as he gets to x equals 1, he's jumping onto a different line. Right? So what's that going to look like? Well, like that. Right? You see the red line corresponds to that part, doesn't it? Right? The blue line corresponds to that part.
So it's asking us at what point do they cross?
Well, it's not really asking you anything. It's just telling you, if we're graphing it, this is the graph of that piecewise function. Now, that's an important piece of it, is where is the boundary between the two, right?
Okay.
And that's always going to be, well, there's the x value, right? If we look at the x value where we're switching, it's at x equals 1. So that's where we know that we're going to make this jump. Yes, ma'am?
Oh, it's always gonna be the same numbers.
Yes, they would have to be the same numbers if it's a piecewise function, yeah. Now, if they weren't, if this one, well, okay, here's a possibility. This is not likely, but what if the top one was a 1 and the bottom one was a 2? That would just mean that there would be a gap in the function where it wouldn't even be defined. You'd have to jump over that gap. But typically, that's not the case. Typically, in piecewise functions, they're gonna be the same. Yeah, good question.
Is there any number that can't?
No, there's no number that the boundary that couldn't be. No number. Yes.
So anytime x is less than 1, it's gonna be z. It's gonna,
Yep.
they're all gonna have the same graph. Like a number.
Yes, right. Because now think about this. Think about this in terms of these ants. As the ant walks along, when he's on the red part of the graph, that's what he's experiencing. And maybe there's a fog in there, and he can't even see what's going on. He might be surprised when he walks up and steps onto the blue function. Okay. Now go ahead. Question.
I was just gonna ask, like, you know how one slope is positive, one slope is negative?
Mhm.
Can they both be positive?
Sure. They could be the same for that matter. It's the lines. These lines could be. There's really no necessary relationship between the blue line and the red line. We'll call it for now. The left and the right. None at all. They could be completely different behaviors. Okay, and they don't both have to be lines. I mean, for now, we're going to treat them as lines, but really we could have stuff going on like this too. We could have something like, well, look, before I jump into this idea, I want to make one more important point here. If we're looking at just the red line, and we'll see another example of this here in a second, but what do we do when we're dealing with an interval where the endpoint is not included? So if we're just talking about the red line only, it's defined when x is less than 1. So as the ant walks along from like -10 up towards +1, when he gets to the end of that red behavior, what kind of a red endpoint should I put on there? Should it be open or closed? It should be open, yeah. Does everybody see that? That's important. That should be an open red dot because the endpoint is not defined on the red function, right? Okay, but now it just so happens in this case that, in this example, that the red endpoint, the red open endpoint, is filled in by a blue solid endpoint. Does that make sense? Because the blue interval does include the equal sign, right? And so we fill that in, and this was nice and convenient for our ant because the two endpoints joined up. You didn't have to jump, right?
Is the other one, like with the inequality, the top one
No, can't be. It can't be, because if that were the case, now, technically, I guess you could make the argument that as long as they join up, it could be. But we never like to do that, because what if they don't join up? Here's my point. And I'm going to cover 2 points at once here. I brought up the idea of what if they're not lines. They don't have to be. This top one could be, for example, a parabola that does that, and then it stops. And the bottom one maybe is like a square root function. Okay, but if they don't line up, so it looks like that instead, if I filled those both in, would this be a function? It wouldn't be, because those points would overlap vertically, and they'd flunk the vertical line test, right? Make sense? So they can't. So that's a very good question. So one of these will always be defined as an equal to inequality, and the other one will not, depending on which one gets the closed end point and which one is forced to have the open end point. Okay? Make sense? Very good questions. Okay, let's move a little further with this. So we call x equals 1 the breaking point. And what I would encourage you to do here, at least initially when you're drawing these things, this is really handy, is to go ahead and put like a light dashed vertical line on the graph paper that reminds you where is that breaking point. So then when you're sketching these things, and I'd like you to do that, by the way. This assignment was a bear. It took hours and hours and hours. But what I'd like you to do when you're trying to match up piecewise functions to the graphs, I'd like you to, on a piece of graph paper, to just do a sketch of that. To get used to the idea of sketching the graph and then compare it to the real one. Does that make sense? Okay. Question?
Is this gonna be on the test?
No. Test Monday is going to be, that's kind of the older stuff. That's only up really just chapter 1 stuff. Yeah, this will be on the next one, which is coming up shortly. We'll do it next week. We'll be through with all this stuff, like midweek next week. So there's our breaking point. Okay, the equation to the left is the top one, like we said. To the right is the bottom one. And if you draw in that little vertical breaking point line, it makes it really easy to do this. Okay, so what about this guy if we want to graph it? Let's go through the process of graphing this thing. What should I probably do first? Breaking point, yeah. Where's that going to be? 2, at x equals 2. Now that's a vertical line, isn't it? If I say the line x equals 2, that's a vertical line. So let's add that first. There's my breaking point at x equals 2. Now, which one goes on the right in this case, and which one goes on the left?
The top and on the left.
Top one's on the right.
Top one's on the right because its x is greater than, right?
Yeah.
Bottom one's on the left because its x is less than or equal to. Okay, so then if I want to graph these things, let's for a second, let's just look at that, arbitrarily, let's pick the top one. How do I graph that line? 2/3 x plus 2/3. If y, and let's just we'll make that one, how about red? So this guy's going to be red. So over on this side, and what I'd encourage you to do is then literally just write the equation on the side of the breaking point where it's going to be graphed. So I didn't give myself enough room to do that. So over here we've got y equals 2/3 x plus 2/3. Yes. Okay, suggestions. What do you think? How could I graph that line? How could I sketch that line? Trent, do you have an idea?
No. Well, the slope would obviously be 2/3, but
Slope's 2/3, that's correct.
so it should start on 1.1, 1, for 1 point.
Okay, so good. Now, when we're going to just kind of, first of all, let's go back to basics. When we're going to sketch a line, how do we always sketch the graph of a line? Well, we could. We could use y-intercept. We don't necessarily have to. If we're going to sketch a line, lines are really simple. They're just straight, right? What do I need to define a line? It's pretty simple. If I want to draw a line, I just need what first? I mean, that's a really kind of bad question. A line is defined by how many points? Let me say that instead. 2. I only need 2 points, right? And that's always our strategy. If I can just come up with 2 points, I can just connect and extend and draw my line, right? So I gotta get my 2 points. Well, a lot of times we'll get the 2 points with the y-intercept and make a little slope triangle to get the other one. But that's not always convenient. Now in this case, and you guys this is such an advanced class, we're gonna think about this out. I'm gonna force you to think about this in kind of a sophisticated way. Quick question, yep.
Okay, the way I see it is, the reason why 1 point on the line would be 1, 1, is because its starting point would be 2/3, if you think about it, because.
That's a good idea. What Trenton's saying, that's kind of what I was getting at. Trenton saw something here. If I were to make like a t-table, and that's really convenient to do. If I make a t-table here with x values and y values, I only need 2 of them, right? What he saw was, if I pick an x value of 1, whoops, actually, is that gonna work?
No.
Okay, 1's not gonna be so super convenient, because if I pick 1, I'm gonna get 1 times 2/3 plus 2/3 is 4/3. It's gonna work, but wouldn't we rather, if possible, and maybe it's not possible, but if it is, could we get a point that that's gonna have an integer result, right? We're gonna get a nice convenient point with an integer x value and an integer y value. So you put it right at
X
a
be
corner.
2/3 too.
Say it again?
Couldn't X be 2/3 too?
Yeah, but then I'm not over, I wanna be, put it this way, at a corner of the graph paper, where both x and y are integers, if possible. Sometimes it's just not possible, or it's really inconvenient. But here we could do it.
If both lines meet at 2, can you just use 2?
Well, we could. I could put 2 in, yeah, that's fine. Does 2 work? I mean, that's not a bad point to pick. If I put 2 in there, what's 2/3 times 2?
4/3.
Plus 2/3? What's that? 2. Okay, so that is a good point. If I pick x to equal 2, I get y to equal 2, and so that is a point that we can use, right? Okay, now, is that point, could I have used a point even over here?
Yeah.
I could have, but I'm just not gonna graph the line there, right? Does that make sense?
Yeah.
Okay. I mean, I could have, if I wanted to, I could have picked like -1 and gotten 0 for an answer, right? And I could have put a little dot there that I'm gonna use to line up my ruler, metaphorically speaking, right?
Yeah.
But we picked the point 2, 2, that's fine. Now, that's a point that I gotta be a little bit careful with. Look at our domain of the top function. X is greater than 2, so what kind of dot should I make at 2, 2? Open one, right? Because that is my endpoint, but it's an open endpoint. Does that make sense?
Yeah.
Okay, so we're gonna do that. Now, what's a really easy way to get another point?
Is the slope.
Yeah, make a slope. Use the slope triangle, right? If we know that the slope is 2/3, why not just rise by 2
Or is.
and run by 3 and get another point right there, right?
Yeah.
Make sense? Okay, so and that's gonna continue on, that's in the way, but it continues on to the right forever. Okay, make sense? Good, so we got the right part taken care of. What about the left part? Make that blue. Okay, so over here to the right of our boundary, we've got the line y equals -x plus 1. That's a pretty easy one to do, isn't it? What's probably the easiest way to graph that one?
Just enter to the negative.
Okay, so, well, the y-axis is actually included in the left region, isn't it? So why not just start with the y-intercept? It's a nice number, it's a 1. So the y-intercept is at 1, and the slope is -1. So I'll just go down 1 and over 1, right, to get my second point.
Yeah.
And I'll just connect and extend, like so. What kind of endpoint do I put?
A circle.
Solid, good. Solid because of the type of
So it
inequality.
doesn't.
So it doesn't always land on the same.
No, doesn't. So in this case, the ant better be a good athlete, because he's got to walk down here and jump up to this line and keep going, right?
So, but I thought you said if you do that, then it doesn't.
Okay,
Oh, never mind.
you see the difference? Now, if these were both solid, it would, but because this one's open, we're okay. The function is still only defined at one point there. Make sense? Okay? All right. Okay, just what we got. Okay, what about that? Yikes. That's okay. No big deal. This is just a piecewise function with 4 pieces. Now this is what we call a step function. Why do you suppose we call this a step function? If you look at the function, look at the 4 different behaviors we get. We get y equals 1, y equals 2, y equals 3, and y equals 4. Okay, go ahead, question?
I thought you said they would be different numbers.
They're not. They're not. Look at this. They're actually not, because look, the endpoint, the right endpoint of this interval matches up with the left endpoint of this one. See what I'm saying? Okay, and if we keep going with that, the right endpoint of this guy matches up with the left endpoint of that one, and so on and so forth. Okay. But my point is, if we were to graph this thing, I think I had a question here first. Yes, ma'am?
Oh, sorry, I have a question about the last.
Oh, okay. Yeah, I can go back.
Sorry.
Okay. There.
How did we use 2, 2 as a point for the top, the line on the right?
Okay, good question.
If x is greater than 2.
Okay.
It's not 2.
Okay, good question. Because I can use that to define the shape of the line, can't I? Right? Because if I want to define the shape of this red line, I just need to have 2 points to get the slope right. Does that make sense? Okay, so this is a point that's perfectly usable, because if it weren't a piecewise function, this top line would have a point, whoops, darn it, would have a point here and a point there, and we would have just drawn it forever, right?
Yeah,
Okay,
but
right, but it's like we've drawn it forever, and now we're just going to erase it. Right now, we're just going to go back and erase everything up to that spot, right? But the line hasn't changed. It's just where the pencil gets put down that matters. Okay, see what I'm saying? And so this point, because it's got an open circle on it, it's fine, because that's telling us that it's not actually part of the line. Now, we could have even used this point and this point to line up the ruler, right? So does that make sense? We're lining up the ruler, but then I'm only going to put my pen down right there and graph.
yeah, but if it's not part of the line, then how can we use 2, 2 as a point on the line?
Because it's irrelevant if it's part of the extended line if we're only graphing it from 2 onward. You see, what this is telling us is, now think about this in 2 pieces. It's a very good question. This is telling us what the extended line is. Right? That's just the equation of a line without any restrictions. What this is doing right here, though, this is the restriction. That's telling us where we can put our pencil down. But to define the line, we can use this point because we didn't fill it in. Right? So that means that it's actually not part of this. It's open circle means it's just an endpoint. Does that make sense?
Yeah, so it's like part on the line except we cut the line.
Exactly. Yeah, exactly. Yes, sir.
The next question it was going to so I was just.
Oh, okay, gotcha. Okay,
Wait, I
so
don't know this one.
what's that?
I have a question.
Okay.
So, what makes you, like, how do you figure out the 2 at the end? How would you figure out that that's the endpoint or boundary?
You don't. That's just given to us.
Oh.
Yeah, that's just, there's nothing for you to figure out. That's, if we're given this piecewise function and we're supposed to graph it, that's how we do it. Okay? Other questions on this slide? Okay. Okay, so this guy. Okay, yes, sir.
Wouldn't that be like straight? I can't remember what it's called.
Yeah, it is. If you look at these behaviors, y equals 1, y equals 2, y equals 3, y equals 4, those are boring. Those are horizontal lines, right?
So they don't need.
So, well, they're horizontal lines, but it's restricted where we can put the pencil down, and this is what Cammie was talking about. So if I graph this guy, look what we're going to do. We're going to take, now everybody watch this closely, because this is exactly what you were talking about. If I take that first function, we'll make this one blue for whatever reason. Whoops. Maybe. We'll make this guy blue. If I'm going to graph the line y equals 1, well, y equals 1 just looks like this, doesn't it? that make sense? So that's the shape of that line, y equals 1, but the restriction says that we can only graph it on this interval. If I can only graph it where x is greater than or equal to 0 and less than 1, where do I have to actually put my pencil down along that line? Okay, I'm going to start at x equals 0, right? Is that an open or closed endpoint? Closed. And I'm going to move to the right until I get to x equals 1, and then what? Right?
Yeah.
So the dark blue is what actually gets graphed, even though the light blue is the shape of the line.
Wait, so so you don't?
So we don't here, because look, that one it's open. Yes, ma'am.
So x is like any possible point that is on that line?
Yeah, it is. Now, so when you're looking at these piecewise functions, the idea is that you're always going to kind of break them up into two parts. Okay, we've got that's not beautiful, let's try this color. We've got the left part, which are the equations, right? That's telling us the shapes of the lines. And then we've got the domains on the right, which tell us where each of those behaviors is defined, where they get graphed. So you read these things horizontally from left to right, but there's always two parts. What's the shape of the line, but where do I put my pen down? Yes, sir.
X is only in that equation though, like it's only in.
Well, it's not, you're right. So on this interval right here, we're just graphing the line. F of x is just a fancy name for y, right?
Yeah.
So we're just graphing the line y equals 1, which is just a boring line that's just got a slope of 0 and a y-intercept of 1, right? Y equals a constant is a horizontal line, remember? Yes?
Could your boundary line ever be like that?
No, can't be. Your boundary line can't be diagonal for a piecewise function because then that would allow us to have pieces that overlap. It wouldn't be a function then, okay? So then what happens when we shift gears? Let's go to, we'll make this one red. So now I've got the line. What color do I want here? I guess, I don't have a good.
Wouldn't the starting point orange? Wouldn't you want to be filled in to open?
Yes. Okay, but the shape of that line is y equals 2. So it's going to be a line like this, right? But we're only going to fill it in where? Well, we're going to fill it in from x equals greater than or equal to 1. So we got to fill, does that make sense? I didn't say that very well, but you get the idea? Up to but not including 2. So that's the part that gets filled in, right?
So if the points don't touch, what are they called?
What do you mean?
What's the reason of having them open or closed?
Well, that's because of the domain. Because you see here we've got a less than or equal to. So because it could be equal to.
So what happens when one's domain and one's other?
That. One endpoint is closed and one's open.
Two endpoints, one's open, one's closed. What would you call it then when they match up?
Like that right there?
Yeah. No, like they're on the same.
Oh, then the pieces just meet. That's all. Yeah, like that first one we looked at. Yeah. Okay, so let's just continue with this one. Then, real quick, the next behavior is going to be y equals 3. So wouldn't you agree that's a horizontal line at 3?
Yes.
But we're only going to graph it when x is greater than or equal to 2, so solid, and less than, so not solid, 3. I'm just making a stair step, aren't I? Right? That's why we call this a step function. Yep. Good. Questions?
So I still don't understand what's in a y. F of x would tell you what makes this equation.
That's what you're graphing. This is the equation y equals 1.
Are we gonna be plugging numbers into these at all, or what? Just.
Well,
Like, we
I mean,
would
maybe
never-
if you're evaluating it, but this is just like saying if I were to,
graphing the lines, that's it.
yeah, right now we're just graphing it. Yeah, that's what we're doing now is graphing a piecewise function.
I just didn't understand what makes them affected by x.
Well, these are, in this case,
Besides x being in y,
which is that's the only thing. That's the only thing, because the x's would normally go there, but these are just constant functions, so there aren't x's. But usually there'd be some slope there, and so there would be an x in the behavior, right? Okay, so let's take a quick look at this. Got a couple more things I want to get through. Okay, so we got a piecewise function, right? Looks like this. Each of those 4 behaviors produces a different step on this step function. Okay, so is that seriously us?
Yeah.
Oh, wow. Okay. Alrighty. Well, we'll finish this up. I'm still going to give you the assignment. It's up, ready to go. Why don't you start on that this weekend? What's that?
When is it?
I'll give you till like Tuesday or Wednesday or something. Yeah.
Yeah, Saturday night.